In this problem, we're told about a 500-gram sample of a radioactive isotope, radium, and it's decaying. That means over time there will be less and less of this, and the amount is subject to this differential equation. So it's changing over time, and it's changing according to this relationship. The rate of change of the amount present at any time is going to be equal to some multiple of the amount present at that time. So the rate at which it's changing is some multiple of how much is there. That's what this says. And our goal here is to find a function that satisfies this and that also satisfies this other information. So A is the amount of time after t years. That means A is our function's name, the dependent variable, and t is the independent variable. And we're trying to find the value of r, this constant that's in here, such that the amount of radium will be 400 grams after 5 years. All right. So we can translate immediately some of this information to the notation in the problem. That first piece is telling me that the amount at time 0 must be 500. That's what time t equals 0 would be the initial or the starting value. And it's also telling us that the amount, this piece here is telling us that the amount at time 5 must be equal to 400 grams. All right. Now, the question is, what function is A? If I can find the function of A, then maybe I can use these pieces of information to find the value of r. So our goal is now to find some function that satisfies this differential equation. That means I need to find some function whose derivative with respect to t is equal to r, which is some constant, times the function that I started with. And you've probably seen this differential equation before. This is the same one that occurs in continuously compounded interest rate accounts. The solution to this differential equation is something like p e to the rt, where this r is the r in the problem, and p is the initial amount. In the banking of problems, that would be the principal. All right. And just as a quick check here to make sure that works, I'm going to take the derivative of this and show that it actually satisfies the differential equation. So the derivative of A will be equal to the derivative of p e to the rt. P is a constant, so I can pull that out of the way. And the rest of this is an exponential. So in here, I'm going to perform a chain rule. The derivative of e to the rt is e to the rt times the derivative of the exponent. R is a constant, t is the variable, so the derivative of r times t is simply r. And then if I rewrite this once or twice, I can show that it is actually equal to r times a. Now remember what our a was. Our proposed solution to this was p e to the rt. So the question is, can I rewrite this result, the derivative of a, in the form of r times a? So let's pull this r out in front and leave the rest of it sitting where it was, so p e to the rt. And now we can see that this can be written as simply r times a. So the derivative the derivative of a is r times a. All right. So far so good. We now know that the function we're looking for has this form, and now we just have to make sure that it fits this data. At time 0, if I plug 0 into my solution, I get p e to the r times 0, but r times 0 is 0 and e to the 0 is simply 1, so this is p times 1, which is just p, and I need that to be 500. So though it doesn't feel like we did much there, what we've done is shown that in fact the p-value for this problem is 500. All right, which again corresponds to our notion that it's the initial amount or the principal if we were viewing this as a banking problem. So now I can update my equation by putting in what I know. The p is 500 and the rest of it is e to the rt. I still don't know the value of r yet, and in fact that's what they're asking for in this problem. So let's see if we can use our second piece of data to find out the value for R. Let's just plug in what we know and solve for what we don't know. The amount that I want to end up with is 400, and the time that should make that happen is 5. So we must have 400 equaling 500 e to the r times 5. And now what I'll do is just solve for r. So we kick over to our exponential algebra techniques. I'll isolate the exponential by dividing the 500 off. 400 divided by 500 would be 4/5. All right, cleaning that up. And this side is just e to the r times 5. I'll write it as 5r. All right. Now that I've isolated my exponential, I'll apply the log to both sides to knock the 5r down out of there. And I'll use the natural log since I've got a base e exponential in this problem. The natural log of 4/5 must then be equal to the natural log of e to the 5r, which is simply 5r. And I now have a linear equation in r, so I can solve for r just by dividing the 5 off. So the value of r that works is the natural log of 4/5 divided by 5. And the numerical value for that, if you punch these into your calculator, is negative 0.0446. You don't want to round too much. You want to carry out at least 4 decimal places on these. Again, the negative sign was to be expected. We were expecting an exponential decay here, a decay at least. The form being exponential means exponential decay. So a negative rate is what we would need to see. All right. And that was what they were looking for in this problem. But I could now, by incorporating that back into my function, I now can tell you the amount that's there at any time. So a typical follow-up question might be, how much is there after 30 years? Or how much, or when will there be only 100 grams left? To answer those sorts of questions, the function you'll want to play with is the one that we've built up. The amount at any time is 500 e to the minus 0.0446 t. And I can use this now to accomplish many other tasks in terms of finding out how this radium is changing, the amount of the radium is changing over time.